of the mixture, right? And there actually we ended and start from there. So, so equation of state, I have discussed for the van der Waals equation of state, and you can see that there are two parameters, A and B, right? See, ideal gas, no problem, PV goes to RT. So there are so ideal gas and ideal gas mixture will behave the same way. PV equals to measure the pressure, measure volume, measure temperature, job is done. So ideal gas mixture will behave the same way, same equation of state. For the real gas, you have two parameters, A and B. For example, the van der Waals equation of state, P plus A by V square, B minus B by B minus B equals to RT. And A and B, they are the very important factors. What is A? A is basically for the interaction. If you remember the correction factors for the van der Waals equation of state, that A by V square the pressure correction. What does it mean? The molecules will be attracting towards each other and repulsive force, and because of that, the actual pressure will be less. Okay, so we have to actually add some of the part to have the pressure correction, and because of the molecular volume, if it is closely packed, the space for the motion of the molecules will be less. And what is the actual volume? It will be V minus B. This is the pressure volume correction. And then it is said that for the mixture, it depends on the other molecules, not a particular molecule. There are different kind of molecules will be there. So that's why B mix has been defined. And the B mix is nothing but summation Bjx, very straightforward. X is the mole fraction, and Bj for the each molecules. For example, you have A gas, B gas, C gas, D gas. For each molecule, you have the Bj is the volume, and A is the interaction depending on interaction parameter, and that depends on the pair-wise interaction, because there are two different molecules. They will be having different attraction level. So if I see that the AI is depending on the pair-wise interaction, and you have to take an all possible combination of the pair-wise interaction. So for any real gas mixture equation will be changed because of A and B. Ideal gas mixture, the same equation, PV equals to 1. So equation of state part has been fixed. I am just going sequentially what we have done to the pure substance. Remember that after this equation of state, we went to departure, right? So now, before going to departure, we have to talk more on this quantity, which is, for example, Vi and Vi bar. This talks about the pure component. This talks about the ith component and mixture. This talks about the pure component. Pure component I, and this is ith component. Ith component in a mixture. Remember that in a mixture you cannot write Vi. It should be Vi bar, the partial molar property. So we have understood Vi bar, we have done the derivations, we have talked about these equations and so and so. But when we talk about for example, we discussed last class, say delta H mix. What is that? Capital H mix. If we talk about I equals to 1 to n, and then Hi Ni minus Ni Hi or Hi1 Ni Hi, right? Final minus initial. And we talked about I equals to 1 to n Ni and Hi bar minus H. Correct? The question is, this how it will behave for temperature and pressure. So when you talk about departure, this will be very crucial. This is very crucial. So we want to learn more on the pressure, temperature, dependency, whether when you have IgM, for example, if you have ideal gas mixture, what actually will happen? It will be IgM, and this will be Ig, because pure component cannot be Ig. So this will be IgM again, and this will be Ig. My question is, even any property, for example, property M, delta M mix Ni, Mi is the specific property, Mi bar is the specific partial polar property, Mi is the specific property, partial polar property, specific property. My question is, Mi bar Ig equals to Mi Ig all the time? Yes or no? mi bar IgM, I am putting a question. All the time mi Ig? We'll see. It may not. It may not be. That's what I'm saying. We'll see. That's the thing I'm going to address. If we resolve this part, you need to resolve this part. Once you resolve the part, then you go to departure. Remember that I am exactly following the class notes, sequential note. If in the pure substance, you can see that I am just going sequential. Because whatever you have done for pure substance, even up to fugacity, we will do up to fugacity. Again we will do here fugacity. Then we will go to multi-component multi-phase. Again same thing we will do there. Because basic thing is a pure substance. Once you learn pure substance should be applicable, it should be extended amicably for the multi-component pure single phase, multi-component multi-phase. So after that we will go to departure. After that we will go to departure. So the question is, when you talked about this, mi bar I equals to mi Ig, apparently it looks like the same, right? Apparently it looks like same, but it may not. Apparently it looks like it is same, but it is not the same. So let's look at the departure. Before getting into the details, I want to look at the departure properties. H minus Hij. I just want to relook that part. T1 V1, which is also H minus Hij T1 P1. Remember that departure formula will not be changed for H and U. It will be changed for S, A and G. So it is nothing but the formula is Z1 minus 1 T1 plus V tending to infinity to V1 P into dou P V1 minus P P1 V. Okay. Similarly, you can have the formula for S minus Sig Tp, S minus Sig Tv separately. Okay. So S minus Sig Tp, if you want to write, I won't write Tv formula. You can always do that if you know the Tp formula, because one extra term will be there for T1 P1, which will not be there for the Tp. And then mod of Z1 V tending to infinity to V1 dou T at fixed V minus R by V, and this term will not be there for TV plane, right? That's what we have done already. So this formula, how it will be behaved? This is for the pure substance. This is for the pure substance. For the multi-component mixture, what it will be? For the mixture will behave ideally at p tending to 0. That mixture is termed as Ig or IgM? IgM, because it's mixture. When it's a mixture, it returns Ig. It is IgM. It's a mixture. When it's a mixture at p tending to 0 is termed as IgM, not Ig. It's termed as IgM. It's termed as IgM, not Ig. Right? So, what is the departure formula? At least for these two. Other things you can do. You can go back and do that part. So, the same thing. It will be H minus H IgM T1 V1, H minus H IgM T1 P1, and so on. And from the equation of state A and B will be different, and that's where you get the departure formula. With respect to Ig, that is with respect to Ig. The similar formula. You get similar formula. Similar formula with H minus H IgM T1 V1 and S minus S IgM T1 P1 and so on. Okay? That's it. I will discuss the mixture. We have a right question. We can have a component basis. We can have the mixture basis. That we will discuss. Maybe I will do in a class the mixture. I will ask in the exam component. Okay. I will do very detailed derivation here. lot of time and invested. It is not that straightforward because this departure formula may be same. My question is how to calculate delta H, how to calculate delta S. Remember, right? Departure formula used for what? To calculate enthalpy change, to calculate entropy change, to calculate internal energy change. Right? That's why you use departure formula. If you have the class note handy. That's the way you have departure formula. Okay? How to calculate delta H means delta X means. Delta H means delta X means. Okay? Please don't confuse with this. I am talking from the T1 P1 to T2 P2. Delta H means H T2 P2 minus H T1 P1. This means from the same particular temperature pressure, if I have a pure component, I'll separate because I'll add it up, get mixture, first change. There are two different changes. When I talk about the departure, it is like T2 P2 minus T1 P1, right? H T2 P2 minus H T1 P1 is delta H, right? Correct? Yes? Okay. Let's proceed. After that, I have to. This is a very critical issue. It looks same. It is same or not, we don't know. And what is the difference? You have small beaker, you have ion component, and you have a big beaker pouring it here. It is Ig, this is IgM. And now it is saying that must be same at P tending to 0. We will proceed further. Okay? Let's see how to address that part. So we'll talk about Ig versus IgM. Ig versus IgM. Okay. Ig we have seen, U is function of temperature, UIG. Right? I'm just going back to the class note. Hig function of temperature. Sig function of temperature pressure. Similarly, we have Gig, which is G hat. Correct? Okay. We know that d mu equals to dg minus sdt plus vd. Generally speaking, dg equals to minus sdt plus vdt plus mu dn for the pure substance. Am I correct? This mu is often replaced by g. Can be because mu and g same. Because somebody was asking, somebody got confused in your class. I said this is not mu, this is capital G. G is nothing but capital G yn. That's equals to mu. When you divide by n, not divide by n, when you take the derivative, what actually happens? It becomes dg minus sdt plus vdp. This will not have any role because this is specific property. It is nothing but a function of temperature, pressure. Mole will not come for the pure substance. Multi-component substance, dg minus sdt plus vdp summation I mu I dni. We have dg minus sdt plus vdp, it should be capital G, sorry, plus summation I equals to j equals to 1 to c minus 1 mu j star dxj, and this is you can write d mu. All fundas here, all fundas are there. See the fundas here. Remember that is mu, this is mu j star. All conceptual things. Once you miss the concept, everything is gone. Once you miss the concept, everything is gone. Right? So this is the part I wanted to clear. Mu and small g are same, not the capital G. Capital G is going into the mu. You only can divide capital G by N, then only you can get mu. But capital G, you cannot say capital mu. Nothing is like that. Okay? Good. So this part is clear. I want to clarify this issue here before proceeding further. So dv equals d0 minus sdt plus v dp. This is our expression, and at constant temperature, you can write d mu equals to plus v dp at constant temperature. And from here we can get, actually what I am doing at constant, I am fixing the temperature, so that when I integrate it, what will you get? Mu equals to mu ig mu 0t plus RT ln P. That means if I integrate it, if I say mu ig, d mu ig, which is Vig RT by P, RT ln P, integration constant is C, then integration constant is not the function of pressure. What else is remaining? Temperature. That's why it is mu 0t. So this is valid for the ideal gas, and this is called a fundamental relationship. This is called as fundamental relationship. This is called as fundamental relationship. Okay. So mu I equals to mu 0t plus RT ln P. You might have seen this expression already. Mu ig equals to mu 0t plus RT ln P. This is, and with that we'll start and see, and this kind of expression can be extended for the ideal gas mixture as well. So proceed the Ig part. I am not starting the IgM part. So this suggests that mu Ig is nothing but temperature and pressure. What we have done earlier, this is also suggesting that mu Ig. So actually fundamental relationship should be based on the what we have actually obtained earlier. Okay, so mu Ig is nothing but mu hat T. Okay, so if we talk about Sig means what? This is that it should be minus dou U by dou T at fixed pressure. At fixed pressure, what should you write from the fundamental relationship, which is mu 0t plus RT ln P at fixed P? What should we write next? The function of Tp both, right? Because if you mu 0 prime, something will be there. Dt. Correct, right? Yeah. Dou T of mu 0t RT ln P, and so you can see that there are two terms will be coming for the second term. The first term you have a mu 0 prime, and you have the discrete function of temperature and pressure. From this, you should be able to have U hat T. So that's the fundamental relationship. What I am trying to say that this is my basic relationship. From there, you should be able to establish all this. Can you prove U is the function of T from this fundamental relationship? U is the function of T. Uig. What is Uig? Uig, we can say that Gig, which is Uig plus PVIG we can say TSIG. So Uig is Gig minus PVIG plus TSIG, which is, this is nothing but mu Ig, which is mu 0t plus RT ln P. PVIG means what? PVIG plus TSIG. What is TSIG? SIG, which is SIG means d mu. So it is d mu 0 t by dt, then
at constant t.
Okay, if you want plus t minus Sig, what is that? It should be minus rho t of mu at constant t. Am I correct? Yes. So what will you get final expression? Tell me. You will get the final expression. Now you can get the final expression. You plug it in the here. Mu equals to mu 0 t plus RT and p. If you do that, you get a very cute expression.
So mu 0 t minus RT.
Mu 0 t
minus RT
minus RT
minus t dou mu
t
by dou t at constant
t d 0 t
dou t at constant t.
at constant
T.
Correct? Yes. That says that what it says, this is function of temperature, this is function of temperature, this is constant pressure, also function of temperature, right? So this is function of temperature, correct? This is function of temperature, this is temperature, this is, of course, mu is a function of temperature. Constant p if you write, don't write, doesn't matter. The function of temperature only. That's the equation constant is. Okay? So it says that you have, what is that? Correct? So similarly you can do for HIG. HIG is very straightforward. HIG is very straightforward. UIG plus PBIG you can say. It will be just like you have minus RTIG, and that is again function of temperature. Okay? So everything has been done here. So what we base the fundamental relationship. We looked a different way. We looked this a fundamental relationship, and with that we found gentle stuff. Okay? That means without deriving, you had the basic derivation earlier. Without deriving, based on this fundamental relationship, one can easily find out the variation of UIG, SIG, HIG, AIG, whatever, the entire set, either as a function of temperature or function of temperature and pressure. This analysis is quite useful for IGM. That's why I am doing it. So let's see how we can extend this analysis for IGM. Let's see how we can extend this as this for the IGM. Okay. So let's proceed here. Any confusion? Any doubts? So we'll now do for IGM. Remember that two things we will talk about, mu I IGM and mu I IG. What is mu I IGM? Mu I IGM represents the chemical potential of component I in the mixture. Please note down, mu I IGM represents chemical potential of component I in the mixture. Mu I IG represents chemical potential of a pure component I. Mu I IG represents chemical potential of a pure component I. Mu I IG represents chemical potential of pure component I. Okay? So what's the definition for mu I IGM? So mu I IGM you can write as mu I IG plus RT ln xi. Why? Because we can write mu I IGM similar manner, mu I0 T plus RT ln pxi. The partial pressure. You have learned the Dalton's law of partial pressure, right? So similar expression like this, you have mu I IGM from this mu 0 T, and then for a particular component that P should be replaced by the partial pressure, small pi, that is nothing but P into the mole fraction, P system pressure. Correct? Is the extension of the fundamental relationship. The extension of fundamental relationship for pure substance. The extension of fundamental relationship for the pure substance. So for the pure substance we have mu I, mu g. Total pressure is system pressure. If I take the ith component, it will be the partial pressure. Okay. When you talk about the and this mu I IgM is nothing but partial molar property Gi bar, right? Am I correct? Mu I IgM is nothing but Gi bar. That's why I am interested, because I remember that my promise was Mi bar IgM. This could be Vi, Ui, Hi, Gi, Ai, whatever. This is nothing but your Gi bar. Right? Based on definition. Correct? Yes? That's why I'm not interested about mu IgM. I'm not interested. I want to know what is the difference. Are they same? As my friend said, yes, they are same. That's what I want to see. So Gi bar IgM is mu I0t plus RT takes up. And Gi Ig, it will be mu 0t plus RT. Only one component, no mixture. Pure substance means only one component, no mixture. At the same pressure. Right? So Gi Ig will be mu 0t plus RT. Gi bar IgM is mu 0t plus RT takes up. And you see that second term will make a lot of difference here, and we will discuss that point. Now we understood why the difference you can expect. They are not the same. Right? They are not the same. So this is nothing but, when you talk about the pure component, it will be Gi Ig mu 0t plus RT. Gi bar Ig mu 0t plus RT dx. This mu I0t, you can say that mu I0t, no problem. Pure substance, multi-component substance. And if you write this in terms of mu Ig, you know that now you can see that mu Ig is nothing but mu I0t plus RT. So if you just take it out, RT xi, so mu I0t plus RT pxi will be mu Ig or Gi Ig. So that is, it says that something very interesting. Gi bar IgM equals to Gi Ig plus RT xi. That means it's giving indication. They are not the same. They are different. What's about Ui bar IgM, Ui bar Ui Ig? Are they same or are they different? I have proved only Gi bar IgM is coming from the first principle. Are they same for U? Are they same for V? Are they same for H? But I can show that Ui bar IgM equals to Ui Ig. Hi bar IgM equals to Hi Ig. But other things are not same. Can you tell qualitatively why it is like that? Can you tell qualitatively why?
Functional pressures.
Yes. Functional pressure is coming here. This is a term having functional pressure. This kind of term will not be there for Uig. And that's why Ui bar IgM equals to Uig. Hi bar IgM equals to Hi Ig. But in contrast, Gi bar IgM is not equal to Gig because of pressure dependency. Similarly, Si bar IgM is not equal to Si Ig. Found clear? Okay, so you have the test tubes, you mix it up. Ideal situation, you will see the difference at beginning to zero. They are not the same. Even the distance is quite far. Because the pressure dependency, because the partial pressure makes a role. And thanks to Dalton's law of partial pressure. The Dalton's law of partial pressure is not there. We all know how to evaluate. You don't have the concept of PXI, and that's the problem. So the credit goes completely to Dalton's law of partial pressure. Right? Okay. So we have got very interesting relationship and we will proceed based on these two further to see the other relationship, entropy, partial molar product for entropy and other stuff. So before proceeding further, we will do a lot of derivations here. For the IGL, our equation is dg equals to minus s dt plus v dp plus summation I equals to 1 to c mu I dn. Mu I, this is mu I mixture. Mu I mixture is further defined as dou G, dou Ni, Tp, Nj, J naught equals to 1, which is also Gi bar. Very interesting. We can write dg as minus sdt plus vdp plus summation I equals to 1 to c Gi bar dni. This kind of relationship you cannot write for other properties. If you talk about du, which is TdS minus PdV, you cannot write ui bar dni because ui bar is defined as dou u by dou ni Tp Nj, but that term will be u is mu I, which is defined as dou u by dou n Sv Nj J naught equals to 1. So this is only valid partial molar property for the total peaceful energy. Right? Okay. So mu I mix is this one. So we will be following the exact same procedure. What we have done for the pure substance. So pure substance, our dg equals to d mu equals to minus s dt plus v d pure, and it says that s equals to minus dou mu by dou t at fixed speed, v equals to dou mu by dou p at fixed speed. Correct? For the pure substance again. Remember that this is your fundamental relationship. We have to get the relationship between Si bar IgM and SiIg. How did you get to the pure substance? You took only this relationship. Okay? And then you put all the values, then mu 0 t and proceed further. What will happen for this? So, for the multi-component substance, what should I write? If you start from here, what we can write for the multi-component substance? For the multi-component substance, the relationship d mu equals to, who will tell me? For the multi-component substance, the relationship not round. For the multi-component substance, relationship for the multi-component substance relationship my God, simple thing, combine first and second law, that thing you are not able to tell me. I am just roaming around. You are now nobody was telling that what is the mu part. I am not asking Rahul, I am asking somebody else. For the multi-component substance, d mu equals to, sir, no idea. Minus. Why am I not telling that? Don't allow me to see. If I start repeating the things unnecessarily, I will get tired. My health will go. You don't care about my health. Why I am shouting, I don't know. Because I am doing a teacher's religion. Teacher's religion is what? To teach the students. Students should not care about the teachers. If I shout, if I bark, you should. That's why the entire class is silent. Because you know that this guy is shouting, no income tax for that. He can shout, he will go. Right? So you want to volunteer. So you could have raised your hand, sir. Even if you do wrong, do I shout? I will always correct. Yes, please. At least I am thankful to you because at least you are trying to volunteer. Others are just keeping quiet, enjoying my shouting. Yes, please. Minus what? Capital S, small s. Minus small s dt. Yes. Plus summation I or j. C minus 1. Sir, apply the brain. Yes, then? No, j is there. J star. Don't say xj or nj. You should feel thermodynamics. If you start marking the formula gone, you should feel for that. Again, I am saying. Okay. And then what is this minus s? What is, so this is mixture. What actually happens if I do mu mix by dou p at T n bar? What actually happens? Remember that this S is what? S is dou mu mix by dou p at T x bar. I am saying T n bar. That's what I am saying. You are not applying your brain. It could be V. If it is dou, if I would have written, what is this now? Can you tell me? You are saying V. Dou mu mix by. Yes, sir, I am asking you. You only told me. Yes, tell me. What is this term? Dou mu mix by dou p. Dou
constant T and
T and N. N is there?
X.
Sir, please. I can also tell like that and go from the class. I am asking him. I am asking in bar. See, lot of conceptual things are there. I just cannot put the things. Lot of concept, lot of mathematical fundamentals are there. What should I write? T and bar. When I write T and bar, what should I write? What is mu I mix? Fill in the blanks. Don't say mu mix here. Already it is there. Something else I wanted to write. Remember that what's the difference? T n bar is Tx bar. Think and tell. This says that mu means the function of temperature pressure x1 to xc minus 1. Capital G is nothing but T P n1 to nc. Mu mix is what? Partial molar property G I bar. I am saying dou mu I mix. Dou mu I mix. Dou mu I mix. Mu I mix G I bar. I am writing same thing again and again because I am not able to think about it. What is G I bar? How to define G I bar? Please don't want, you want to volunteer? Yes, madam. Dou G by dou Ni at constant T P N J, J not equals to 1. Okay. What we can do? Remember that you have to get relationship between SI bar Ij and SIG. So, dou Ni, dou G, dou P Tn bar because I'm shifting, and this is Tpnj, j not equals to y. Did you understand the shifting part? Since the thermodynamic property, I can shift. If it is not thermodynamic property, I cannot shift. If I shift, this P's thing is Tn bar, Ni's thing is Tpnj, it will also shift. I have done long back, very beginning. Next step, what we can write? What is dou G dou P? Tn bar. It is there. Dou G dou P. Tn bar is V. Correct? So we have dou V, dou Ni, Tp, Nj, j not equals to y, which is nothing but Vi bar. Right? So we got a very interesting relationship. Dou mu I mix by dou P. See, this dou mu mix is not, it is not a mu I mixture. This mu, okay, plus B. If I have mu I mixture, it is Vi bar, partial molar property. This partial molar property that cannot be obtained from here. You can obtain from this expression. You have the d mu mix. Okay, you can say that, okay, I can write mu I bar and put. You cannot do just like that. You have to evaluate each and every term, because we know that mu I mixture is nothing but function of temperature and pressure, and we can see that how we can. So can you put right dou mu I mixture by dou P at Tn bar. Next we will write dou mu I mixture by dou T at Tn bar. You should tell me. Same word. You should tell me. I won't tell you. Dou mu I mixture at dou T at Tn bar. This I am saying equation number 8. Remember that this thing didn't come in the pure substance. Pure substance came directly. Pure substance, you can see that dou mu mixed by dou P, you could have done directly. Okay, this capital V, small v, and that we put Ig and all. But here, when it goes to multi-component, we have to do this whole lot of derivation. That's the difference. I am teaching every line difference between pure and multi-component. Here, proceed. What you will get? Same direction you proceed. Dou T of dou G dou Ni, Tp Nj, j not equals to y, Tn bar. Then flip the temperature. What will you get? You will get dou Ni of dou G dou T, Tp Tn bar, and outside Tp Nj, j not equals to y. What will you get? Minus Si bar. All of you got it? Yes. Minus Si bar. Okay. So this interesting relationship we got that says that Vi bar Igm is nothing but dou mu I Igm by dou P Tn bar. What is my mu I Igm? It is nothing but mu I Ig plus RT ln Xi. Correct? Mu I Ig. So what did you get? Dou mu Ig by dou P at constant temperature. Second term will be there? Yes or no?
So it will be 0.
0. Why? Vi by Igm is dou mu Igm by dou P. Mu Igm is nothing but mu Ig plus RT ln Xi, and mu Ig is nothing but mu I0 T plus RT ln P.